Yogah Karmasu Kaushalam.
Good morning everyone. I am Nikita Mishra from Department of Chemistry, Gujarat University. Welcome you all in the online refresher course in chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, Gujarat University, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, HRDC, Department of Chemistry, Gujarat University. Welcome you all in the session of Dr. Devang Pandya, Assistant Professor, St. Xavier's College Autonomous, Ahmedabad, Gujarat.
Hello everyone, I am Dr. Devang Pandya, Assistant Professor, Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Would like to thank UGC Human Resource Development Center of Gujarat University for giving me opportunity to connect with you and deliver my session on organometallic chemistry. I would like to thank Professor Dr. Jagdish Joshi sir, the Director of UGC HRDC Gujarat University, and Dr. Dilip Vasawa sir, Course Coordinator, Department of Chemistry, Gujarat University, Ahmedabad, and the entire team of HRDC Gujarat University and team of Department of Chemistry, Gujarat University, Ahmedabad for supporting me for this online refresher course and lecture series. Team HRDC Ahmedabad is very supportive and helpful. I would like to say something regarding HRDC Gujarat University. As you know friends, HRDC Gujarat University is ranked as 15 in India and number 1 in Gujarat. It is pioneer and created history, or we can say a benchmark, by organizing several online programs time to time. Friends, the first of its kind online refresher course in India in the year 2018-19 is given by HRDC Ahmedabad, Gujarat University. About 2,500 participants have attended it. UGC HRDC also have one more feather in their crown. They have organized the first of its kind online annual refresher program in English language teaching through ARPIT with record break 9,000 participants in the year 2019-20. Friends, the first of its kind online annual refresher program in English language teaching again through ARPIT with record break 3,500 participants in the year 2021 during the pandemic as well. Gujarat HRDC Ahmedabad Gujarat University has the first ever online short-term course of e-content development during the lockdown and during the unlock one. More than 130 courses with about 5,000 participants have successfully completed. The participants are from across the country. The first online professional development program for the administrative staff of university during lockdown with 105 participants is successfully organized by UGC HRDC Gujarat University. This institute have the first of its kind PhD coursework for all the registered PhD scholar of Gujarat University has been organized since 2016. The first of its kind PhD coursework is in blended mode, mixed online as well as offline for all the registered PhD scholars of different University of Gujarat, Gujarat University itself, BKNM University, Junagadh, KSKV, Kutch University, Bhuj, and about 900 PhD scholars have successfully completed their coursework through these programs. HRDC Gujarat University is coordinating the online e-content creation training for all the professors of colleges and universities of Gujarat, along with the Department of Higher Education, Commissionerate of Higher Education, and Knowledge Consortium of Gujarat in 2020. Friends, UGC HRDC Gujarat University was funded by MHRD under RUSA by giving the grant of rupees 3.33 crores. It is one of very few HRDC which have very fruitfully and successfully organized the programs under it. It has collaborated with IIM Ahmedabad, SPIPA, IIT Delhi and IIT Mumbai, JNU, Delhi University, the Lal Bahadur Shastri National Academy of Administration, Mussoorie, Mumbai University, Narsi Monji Institute of Management, InflipNet, SNDT, Mumbai University, St. Xavier's College, Mumbai, NIEPA, NCRT, and UGC, etc. The website of UGC HRDC Gujarat University is very dynamic. The journal of UGC HRDC Gujarat University is indexed in cross-reference and has digital object identity, that is DOI, and it invites international resource persons as well. It has MOU with UK and Canadian University. It provides consultancy, and this all is possible under the dynamic leadership of Professor Dr. Jagdish Joshi sir. It is very innovative and established training institute.
Organometallic chemistry is in fact a very complex field, and it is a very fascinating field. What this lecture does is to have a structured introduction to it, so that even if a person has not studied any organometallic chemistry in the earlier days, he can boldly start reading the literature in OMC after going through this lecture. So let us take a look at the presentation slide one by one. We have structured introduction, as I said, but it is definitely a very interesting and fascinating field. The leading journals of the field defined as organometallic compound as one in which there is a bonding interaction, ionic or covalent, localized or delocalized, between one or more carbon atoms of organic group or molecule and a main group transition, lanthanide or actinide metal atom or atoms. Following long-standing tradition, organic derivatives of metalloids such as boron, silicon, germanium, arsenic, and tellurium are also included in this definition. It is also understood that the element to which carbon is bound is more electropositive than carbon in organometallic chemistry. Traditional chemists do not agree to classify metal cyanide complexes as organometallics. It was a latecomer into the subject field of chemistry. It was only in 1956 that people realized that organometallic chemistry is a discipline, subdiscipline of its own, and it has a significant amount of material that would be great interest not just in the laboratories but also in the industry. The problem with organometallic chemistry is the fact that suddenly the student is presented with a large number of new concepts which are not available or necessary to understand organic chemistry, or for that matter even inorganic coordination chemistry, classical coordination chemistry. Now we first answer the question, why study this particular field if it is so complex? If it is interesting, then it must be worth it. So let us take a look at some reasons why we should study organometallic chemistry. For checking the importance of a topic, I have developed here a few questions that one should ask when you look at any new discipline. And the first question that I ask is that, are there any significant discoveries in this field that has merited? For example, the award of a Nobel Prize. Now, at least in the sciences, it is well known that the Nobel Prize is considered as one of the best prizes or one of the top prizes that are given to a scientist who has made a very important discovery which would benefit mankind. And so we can ask this question: has organometallic chemistry really achieved that status so that some people working in this field would receive the Nobel Prize? Let us see what happened to that question. Then we ask the question. We look at some of the journals which are of importance to all scientists working in the area of chemistry. Do we see any organometallic chemistry papers? And what kind of papers are they? Let us see what kind of research is funded, and then finally how much of the economy is really driven by this topic. So each one of these questions will be briefly answered before we proceed to the subject itself. So let us take a look at the Nobel Prizes here. I have listed for you some of the Nobel Prizes that have been awarded in the general area of organometallic chemistry. As I said, the subdiscipline was recognized only in the late 1950s, and surprisingly, by 1963, Ziegler and Natta was awarded the Nobel Prize for working in the area of titanium and zirconium catalyst. These catalysts, which were capable of producing higher molecular weight polymers, especially polythene and polypropylene. And polypropylene was made in a specific fashion which resulted in very interesting and very valuable properties for polypropylene. This area continues in spite of the fact that the major discovery was made in 1963. Even today, it continues to be an active area of research, and through this literature, we will see this, how this is quite important and what a fundamental reaction and organometallic chemistry is responsible for this particular discovery. Next, let us take the Nobel Prize that was awarded to Wilkinson and Fisher in 1973. That comes just 10 years after the first Nobel Prize to Ziegler and Natta and Wilkinson. Wilkinson and Fisher were actually awarded the Nobel Prize for their discovery of metallocene. The discovery was in fact the key discovery that spurred people on to studying organometallic chemistry as a subdiscipline. By then it was very much clear that it was this seminal discovery. The subsequent research work that was done in this area was going to contribute significantly in chemistry. I next talk about the discoveries made by Herbert Brown and Whiting and Lipscomb. Take these two Nobel Prizes together because it turned out that all of them contributed to chemistry of elements on either side of the carbon. Brown contributed to the chemistry of boron, Whiting to the chemistry of phosphorus, which is on the next slide and the right side of the periodic table where carbon is there, chemistry of boron and the structures. These are key discoveries in organometallic chemistry because they helped one to understand some of the structures which were not able or available in the literature in the earliest days. So next comes the discovery or the Nobel Prize to Foucault and Hofmann. Once again, Foucault and Hofmann were given the Nobel Prize for their contribution to the structures of compounds, and they used frontier molecular orbital theory, but Hofmann applied it completely to organometallic compounds. He was able to explain the structures of all the new compounds that were discovered in the 60s and 70s by researchers working in the organometallic chemistry, and also suggest a framework for understanding few structures that would be discovered in the future. So that was a seminal contribution to the field of organometallic chemistry by these people. There was a long gap since from 1981 to 2001, and in 2001 Sharpless, Knowles and Noyori were awarded the Nobel Prize for their contributions to asymmetric catalysis. And this was completely in the field of organometallic chemistry, where chiral ligands were used by these workers to generate chiral compounds, which were very important in the field of drug discovery. So Noyori, Knowles and Sharpless were recognized for their key contribution in 2001. This was rapidly followed by another two Nobel Prizes in 2005 and 2010. And in 2005, Skor, Grubbs and Chauvin were awarded the Nobel Prize for their work on metathesis chemistry. Interestingly, this deals completely with carbon-carbon double bonds and double bond containing compounds, and how they can be transferred from one to other. It turns out that the new bonds that were formed were also double bonds, and so this turns out to be contribution that it is not a parallel in classical organic chemistry. This was followed by Heck, Negishi and Suzuki, who contributed significantly to the formation of a carbon-carbon single bond. These two discoveries in 2005 and 2010. These two Nobel Prizes recognize the contribution of organometallic chemistry to the formation of carbon-carbon single bond and carbon-carbon double bonds. If you look the span of say 50 odd years from 60 years from 1955 to 2010, you'll see that there are about 8 Nobel Prizes that have been awarded to the field of organometallic chemistry. And even earlier, the discovery of Salvarsan, which is inorganic or organometallic drug that was given to treat syphilis, was also someone who received the Nobel Prize for in the field of drug discovery. But then it was an organometallic compound. So you can see that several compound Nobel Prizes have been given in the field. Now let us take a look at briefly at the journals and how they give importance to the subject of organometallic chemistry. Now, if you look at any one of these common journals which are on the top of the list of any researcher, like Journal of American Chemical Society or Chemical Communications or the Angio-Intini, these journals are the journals which are published in the journal area of chemistry, and if you open any issue, you will find that there are at least 2 or 3 articles on organometallic chemistry. So I have put for you in this presentation here just one instance of article written by Shiloh and Shulpin about CH activation. This turns out to be a very important reaction which has been made possible because of organometallic compounds and organometallic chemistry. So you can see that once again, inorganic organometallic chemistry is extremely important in inorganic chemistry and chemistry in general. Once again, early transition metals were shown to be good metals for transition metal CH activation. But recently it was it has been shown that even late transition metals with appropriate set of ligands can carry out ligand directed CH activation reactions, and this work has been carried out by Melaine, Sanford and co-workers. If you look at the field of organic chemistry, it is not as if everything that needs to be discovered has been discovered. So here I have an article which is appeared on journal Nature. You find that they have discovered something extraordinarily new. Even in this last 60 years, what was not known has been newly discovered. Here is an example of a reaction between a molybdenum complex where molybdenum is in the zero oxidation state, and it has got 6 phosphorus ligands around it. So here is a ligand that we are talking about when its metal initially coordinates to the ring where there are 2 nitrogens. So it is a phenazine ring that is having the nitrogen on the aromatic part of the ring, and then after some time, if you heat it further, then the molybdenum moves over to the ring which has got only the carbons. So here are some challenges about why this happens and what are the reasons which initially stabilize the nitrogen containing ring coordinated to the molybdenum, and later what is the thermodynamic preference for the carbon containing ring. Interestingly, if you just move from molybdenum to tungsten, one would expect very similar reactivity, but surprisingly the same reaction which was carried out with tungsten now suggests that the reactivity can extremely different, and you have extraordinarily novel compounds. When an aromatic ring system has been broken and the carbon-carbon ring has been broken, carbon-carbon bond has been broken, and that too part of aromatic ring, and that forms a metal cycle. So here is the set of atoms that we are talking about, and that forms a ring, and that ring turns around or turns out that ring is aromatic ring. To start with, here is a ring and that has been broken by tungsten. You can see that some extraordinarily novel complexes can be generated, something that challenge our understanding of chemistry in general and help us to think about what could be coming in the future. Here is another challenge that has come up very recently in 2005. Graham Ball and co-workers have shown that even xenon, which is in zero group element or an inert gas, what was originally considered as something that would not react with any other element, what was called an inert gases or zero group, that turns out to be an element which can form an organometallic compound. Let us see what they have actually done. Here is the reaction that they have carried out. The rhenium complex, which was excited with a xenon flash lamp, absorb light, and in the excited state loses one of the ligand. If it loses the xenon, if it loses the carbon monoxide, then this xenon appears to coordinate to rhenium. In this particular state, it is possible to see that xenon phosphorus and xenon fluorine coupling constant. So this was carried out by labeling the xenon. So they carried out a reaction in presence of 128 xenon, which is in NMR active, and they are able to show that in fact there is a covalent interaction between the xenon and rhenium. That is the only way in which you can have this type of weak coupling constant between xenon and fluorine. So you can see that there are surprises galore, and there are challenges that have to be addressed in the field of organometallic chemistry. If you ask these two last questions to see what research is funded, how much of it is deriving the industry, once again organometallic chemistry comes out on the top. You can take all the journals that publish organometallics, and you can see that the number of papers published are significantly large, and we can say it is close to 2,400 papers have this concept of organometallic chemistry. Organometallics mentioned in their papers, or if you look at the key papers, if you look at the topics that are mentioned, you can see that organometallics are there in at least 1,400 papers every year. So it turns out that this is a very active field of research. And even if you look at the industry, it looks as if you have a large number of industry which employ organometallic compounds either as catalyst or as additives and as a part of process which is there in the industry. So here I have listed some of the silicons and organolithium compounds. Organolithium compounds are used significantly in fine chemical synthesis. Silicons are used in various industrial applications and their elastomers and so on. Metal complexes are very commonly used for making polymers, especially polypropylene and polyethylene, which are made in tonnage quantities. These molecules are made using organometallic catalysts, which are basically the results of Ziegler-Natta's work. And then there are other small molecules like acetic acid, acetanilide, and several other small molecules which are generated from carbon monoxide, hydrogen, and readily available starting materials. And this is again made possible by organometallic compounds. We will sum of these reactions and how these unique reactions are made possible because of organometallic chemistry. So we have looked at a variety of questions. Are there Nobel Prizes? Are there important papers published in journals? Is this research well funded? And what is practiced in the industry? In all these cases, we have come up with positive answers for the field of organometallic chemistry. So now you have come up with the answer of why is the subject important. But still we need to find out, are we dealing with a special element in organometallic chemistry? That would be in our next slide. Yes, you can see that elements in the shaded area are the metals of organometallic chemistry, and organometallic chemistry deals with these large number of metal ions in this periodic table, which is in the shaded area. So now let's define this organometallic field. The compounds containing at least one direct metal carbon bond are called organometallic compounds. Metals means less electronegative than carbon. Electronegativity of carbon, as you know, that is 2.5, and electronegativity of silicon, that is 1.8, boron 2.0, arsenic 2.0, germanium 1.8, etc. And the compounds in which metals or metalloids like silicon, boron, germanium, arsenic, etc. are bounded directly to carbon atom, and those all compounds are called organometallic compounds. So you can see the example of few such organometallic compounds. In other words, organoboron, organosilicon, organoarsenic, organotellurium, these are the compounds. These are called organometallic compounds. Phosphorus, which have electronegativity 2.1, is also less electronegative, and the compound containing phosphorus carbon bond should include in organometallic chemistry. That is the question puzzling each time when we look at the definition of organometallic chemistry. But the compound containing phosphorus carbon bond are diversified and numerous. So as a separate branch of chemistry, it is also known as organophosphorus chemistry. So compound like FeCO5, nickel, tetracarbonyl, hexacarbonyl, chromium, etc. are organometallic compounds, although carbon monoxide is not considered as an organic molecule. Similarly, metal carbides, metal cyanides, metal graphite are not included in organometallic chemistry as well. And metal alkoxide, metal amide, chelates, complexes, metal salts of carboxylic acids are not included in organometallic chemistry. As far as classification is concerned, we can classify it in different bases. First one is on the basis of hapticity. So monohapto, that is eta 1 ligands, dihapto, trihapto, tetrahapto, pentahapto, we can say polyhapto ligands would be there, and depending on the hapticity of different carbon attachment with central metal ion, we can classify organometallic chemistry or organometallic compound. On the basis of composition, simple organometallic and mixed organometallic compound, that way we can classify on the basis of its composition, and on the basis of the position of metal in a periodic table, we can classify this as a main group organometallics and D and F block containing organometallic compounds as well. So let us start with the classification on the basis of hapticity. The number of carbon atoms of organic ligands which are directly attached to the metal in organometallic compound is called hapticity of the organic group. The term hapticity derived from the Greek word haptein means fasten or bind. So it will binding of carbon with the metal, and that is in a Greek word known as haptein. The hapticity 1 to 8 have been observed for organic ligands. The hapticity of organic ligand is denoted by eta with appropriate numerical superscript. Say for example, if it is monohapto, it is eta 1 ligand, only one carbon atom directly attached with the metal atom, which is known as monohapto ligands. These are the ligands example which is considered as monohapto ligands. Dihapto, in which the organic ligands whose carbon atoms are closely associated with metal atom, two carbon atoms will going to associate, and these are the example of that one. You can see our best example is J salt, and the J salt hapticity of ethylene is 2, that means two carbons simultaneously attached with the metal center, closely associated with the metal center. Trihaptoligand, that is eta 3 ligand. The organic ligand whose 3 carbon atoms are closely associated with metal. These are the example for that. Pi allyl group is represented by that one. And tetracarbonyl manganese, the hapticity of allyl group is 3, and therefore it is the example of trihaptoligand. Now tetrahaptoligand, in which organic ligands whose 4 carbon atoms are closely associated with metal, and example is cyclobutadiene. You can see here how it is associated, all the 4 carbon attached with the ion. So the hapticity of cyclobutadiene is 4. Pentahaptoligand, the organic ligand whose 5 carbons are closely associated with metal, and we have cyclopentadienyl as an example. I can see in ferrocene hapticity is 5. So hexahaptoligand, that is the organic ligands whose 6 carbon atoms are closely associated with metal atom, and this is the example, that is benzene. And you can see in bis-benzene chromium, where chromium is in zero oxidation state, you can see the hapticity of benzene would be 6. 7 haptoligands, in which the organic ligands whose 7 carbon atoms are closely associated with metal atom, and this is the example for that, tropylium cation, and the hapticity of tropylium cation is 7. Octahapto, that is eta 8 ligands, and the organic ligands whose 8 carbon atoms are closely associated with metal, they are octahaptoligands. The example is cyclooctatetraene dianion, which is aromatic in nature, and uracil, that is also the hapticity of cyclooctatetraene dianion in uracil is 8. On the basis of composition, we have a simple organometallic compound. The organometallic compound which have only hydrocarbon radical or hydrogen atom attached to the metal atom are called simple organometallic compound. We have the example of tetramethyl lead and tetramethyl stannous hydride. These are the example of simple organometallic compound. Simple organometallic compounds are of 2 types. We can see here a symmetrical arrangement where the 2 ligands are similarly attached with or simultaneously attached with the central metal ion, and unsymmetrical where you can see here ethyl part and methyl part attached with this metal ion gives unsymmetrical simple organometallic compound. Mixed organometallic compound, in which you can see the organometallic in which group other than hydrocarbon radicals or hydrogen atoms are also directly attached to the metal atoms are called mixed organometallic compound. Here you can see the example where bromide and methyl going to attach with Mg as a Grignard reagent, and methyl group attached with cyanide chloride, which gives example of mixed organometallic compound. On the basis of the position of metal in periodic table, you can see main group organometallic compound. The organometallic formed by S block and P block elements are considered as main group organometallic compound. We have the example for these methyl lithium, methyl magnesium bromide, tetramethyl lead. These are considered as main group organometallic compound. D and F block organometallic compound, where you can see the organometallic formed by D or either F block elements, and they are called as DF block organometallic compound. The example for that, you can see that D we have ferrocene, and as far as F block is concerned, uracil would be the example of this class. Now, classification of organometallic compound on the basis of nature of the metal carbon bond. You can see here ionic nature. The organometallic compound containing highly electropositive metals such as alkali metals, alkaline earth metals, lanthanides, actinoids, and electronegativity value equal to or less than 1 are mostly ionic in nature. Here the carbon atom is negatively charged and the metal is positively charged in such compound. The main binding force in such organometallic is the electrostatic attractive force acting between the oppositely charged ions. which is non-directional in nature. So you can see the example for that, that is methyl potassium, which has 51% ionic character. Then you can see C5H5, that means cyclopentadienyl. Sodium cyclopentadienyl dienide ion is also an ionic organometallic compound. The organometallic compound of lithium, beryllium and magnesium are appreciably covalent. In most cases, there's a smaller in size, greater charge oblique radius ratio, and hence greater polarizing power of lithium, beryllium and magnesium ions. Sigma bonded covalent organometallic compound. So the organometallic compound in which carbon atom of organic group is attached to the methyl by normal covalent sigma bond. Two-centered or two-center true electron 2C2E bond are classed as sigma bonded covalent organometallic compound. Such compounds are generally formed by p block elements with electronegativity greater than 1 but less than 2.5. So when the electronegativity of the metal elements or block elements would be between 1 and 2.5, we're going to form this class of sigma bonded covalent organometallic compound: tetramethyl boron, tetramethyl aluminum, trimethyl aluminum, trimethyl boron, tetramethyl silicon, tetramethyl lead. These are the example of such organometallic compound. However, d block elements are also capable of forming sigma bonded organometallic compounds. These are the example for d block metal elements containing organometallic compounds. Well, thank you for paying attention to this video lecture. Keep asking question, as you know that asking question is a beautiful way to gain knowledge. Thank you.